Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to the 30th lecture of the course Discrete-time Markov chains and Poisson processes. So, in the last lecture we saw this concept of Poisson thinning, which said that suppose you have some events arriving according to or some events happening according to a Poisson process with rate lambda, and each event you classify as type 1 with probability p and type 2 with probability 1 minus p independent of everything else. Then if you count the number of type 1 events and call it as n1t, and the process counting the number of type 2 events you call it as n2t, then both this n1t and n2t are again Poisson processes with rates lambda p and lambda times 1 minus p respectively. Moreover, these two processes are independent. So, this is what is called Poisson thinning, and using that concept we also solved a problem in last lecture. So, today we will be seeing another problem and a very interesting problem where we will use this concept of Poisson thinning again. So, let us start. So, the problem is quite long, so let us read it carefully. Suppose non-negative offers to buy a house that you want to sell arrive according to a Poisson process with rate lambda. Fine. Now, once the offer is presented to you, you must either accept it or reject it and wait for the next offer. Fine. So, you want to sell a house. So, offers are coming for buying that house. Now, once an offer comes, you will either accept that offer or reject it and wait for the next incoming offer. Fine. Now, suppose you incur a loss at the rate C per unit time until the house is sold. So, until you are able to sell the house, you incur a loss at the rate C per unit time. So, you can think of it as maintenance cost, right? Okay. Now, assume that each offer is the value of a continuous random variable having probability density function small f such that fx is not equal to 0 for all x strictly greater than 0. Obviously, since this is about offer, fx will be 0 for x less than or equal to 0 because an offer cannot be negative, and also you have this assumption that integration 0 to infinity x fx dx is strictly less than c by lambda. So, this is just a technical assumption you need in order to solve this problem. Fine. So, the offers are actually random. So, what will be the amount of the offer? That is random. So, each offer is a random variable, each incoming offer is a random variable which has, it is a continuous random variable which has probability density function small f, right. So, these offers are coming independently of one another, and each offer, the value of each offer is a continuous random variable having probability density function some small f. Fine, where f has certain assumptions that for every x greater than 0 it is non-zero, and another constraint which is this, that 0 to infinity, integration 0 to infinity x fx dx is strictly greater than c over lambda, where c is this rate at which you incur loss. So, c is the rate at which you incur loss and lambda is the rate of arrivals of the offer. Fine. Now, what is your objective? or your aim, your objective is to maximize your expected net return, which is equal to the amount you receive by selling the house minus the total cost incurred. So, you are incurring a cost at a continuous rate, which is C, and then finally, when you are able to sell the house, you get a certain amount. So, what is your net return or net gain? So, it is the amount you get by selling the house minus C times the amount of time you had to wait for selling the house. Fine. Okay. Now, suppose that you employ the strategy of accepting the first offer that is greater than some specified value y. So, you are following a certain strategy. What is the strategy? That you will wait until the first offer which is greater than y. So, you fix a value y, and your strategy is you will wait for the first offer which is greater than or equal to y. If an offer less than that comes, you will not sell. The first time an offer of size greater than or equal to y comes, you accept the offer and sell the house. Fine. So, that is your strategy. Now, what is the based value of y? So, how do you fix your y? That is such that you can maximize your return, right. So, your strategy is you wait until the first offer of size greater than or equal to y. So, what you are trying to find out? You are trying to find out what should be that value of y that I should wait until. Fine. So, what is the optimal value of y? Optimal in what sense? Such that you get the maximal expected net return, where the net return is the amount you receive minus the total cost incurred. So, you are trying to maximize your net return. Fine. So, again, since everything here is random, so you are basically trying to maximize your expected maximal return. So, for what value of y will that be maximized? So, the questions are find that value of y and what is the maximal expected net return for that, but for that optimal value of y. Fine. So, the question is clear. So, now we will try to solve it. Okay. Now, an offer is of size greater than y with probability this. Why? Because you see that offers, so here you have seen that each offer is the value of a continuous random variable having probability density function f dot. So, the probability that the offer will have size greater than y is 1 minus fy, because where f I am thinking of as the, so if fy is probability, so if I say, so it is here, so if say x is the size of the offer, so then that is probability x less than or equal to y. So, 1 minus fy is basically probability that x is greater than y. Fine. So, f I am thinking it as the CDF of offer, right, the cumulative distribution function of the offer, which we know is each offer is a random variable with density function small f. I am calling capital F as the CDF of that. Fine. So, an offer is of size greater than y with this probability, which is 1 minus fy. Now, since this has a density, so if you write it in terms of density, it is integration y to infinity fx dx. Thus, offers of size greater than y arrive according to a Poisson process with rate this. So, here we are using again the concept of Poisson thinning, because each offer will be, an arriving offer will be greater than y with probability 1 minus capital F of y. So, now offers are arriving according to rate lambda. So, here basically you are say think of, you will say an offer is of type 1 if it is greater than y. Fine. So, the rate at which offers of type 1 arrive is lambda times 1 minus f of y. So, here the small p is 1 minus f of y. So, lambda times p. Fine. So, this is where we are using the concept of Poisson thinning, that offers of size greater than y arrive according to a Poisson process with rate lambda times f minus y, because an offer is of size greater than y with probability 1 minus fy, where 1 minus fy is given by this quantity. Fine. Now, therefore, the time until the first arrival of an offer of size greater than y is exponentially distributed with parameter lambda times 1 minus fy. Why? Because offers of size greater than y arrive according to a Poisson process with rate lambda, and you know that its inter-arrival times are exponentially distributed. So, the time or the T1, so you are basically interested in T1 when the first offer of size greater than y will arrive. So, that will have exponential distribution with parameter lambda times 1 minus capital F y. Fine. Now, let x be the size of an offer and let gy denote the net return from a policy that accepts the first offer with size greater than y. Remember, we are interested in the expected net return. So, what is E of gy? That should be the expectation of the accepted offer minus C times the expected time to accept, right? Why? Because by selling a house, you get a certain amount, but you also incur a loss. What is the loss? The loss is C times the amount of time you take to sell the house. So, what is the expected net return? The expected net return is the expected amount you get by selling the house minus C times the expected time to accept the offer. Fine. Now, what should be expectation of this accepted offer? So, it should be expectation of x, but not just expectation of x under the information that x is greater than y, because you have accepted the offer. That means the size of the offer was greater than y. Fine, because that is the strategy that you are following. You will accept an offer only when it is greater than y, or you will accept the first offer which is greater than y. So, now since you are given the information that you have accepted the offer, that is equivalent to giving the information that that particular offer was of size greater than y. So, when you try to find the expectation of the mean of the accepted offer, so it will be a conditional expectation. So, expectation of x given x is greater than y. That follows because you accepted the offer. Minus C times, remember what was the time to accept? So, the time to accept is basically the time until the arrival of the first offer of size greater than y. Now, that has distribution exponential with parameter lambda times 1 minus fy. So, expectation of that will be just 1 over the parameter. So, you get C times C divided by lambda times 1 minus fy. That is expected time to accept. C is just the rate at which you incur the loss. Now, how do I calculate this? Now, what is expectation of x given some event A? It is basically, so you integrate the density or the of x on the set A on the event A divided by probability of A. So, here what is the event? Event is x is greater than y. So, here you should integrate it from y to infinity and not from 0 to infinity because of this conditioning that x is greater than y. So, because you see while calculating a conditional expectation, you integrate only over the given event. So, here the event is x is greater than y. So, you have integrated it from y to infinity, and then the probability of A. So, here is x greater than y, probability x greater than y is just 1 minus fy, because we have assumed that f is the CDF of x. Fine. So, you get this. Now, if you just write it in a compact form, you get this. Fine. So, that gives you the expected net return when you are following a policy that you accept the first offer of size greater than y. Now, what you are trying to do in this problem? You are trying to find the optimal value of y. Optimal in what sense? The optimal in the sense that the value of y which will maximize your expected net return. Now, so if you have to maximize a function, then or if you want to find the point where a function is maximized, what do? You differentiate the function and put equal to 0, put the derivative equal to 0. So, we do that same thing. So, this is an elementary fact from calculus. From you must have learned this when you learned about maxima minima. So, if you want to find the point where a function is maximized, you differentiate the function and then equate it to 0, then the value or the argument where it is equal to 0, that is the point where it is maximized or minimized. But anyway, so if you have to find the maximum, then you need to differentiate the function and put equal to 0. So, that is what we do here. So, we differentiate this e of gy and equate it to 0. Now, if you do the derivative and then equate it to 0, you will see that this is equal to 0 if and only if this quantity is equal to 0. So, again this calculation you can easily do. You have to just simply differentiate this quantity with respect to the variable y. So, here y is the variable, fine. Okay. So, if you so the derivative of e of gy is equal to 0 if and only if this condition is true. So, the optimal value of y will satisfy this relation. So, you do not get very explicitly, but you get it in terms of this relation. So, the optimal value of y should satisfy this relation. So, thus the optimal value of y, let us call it as y star, should satisfy this relation. So, which we get it from here. So, I just take this thing to the other side and then we get this, fine. Now, what is 1 minus f y star? Remember, f is the CDF and the random variable has a density. So, 1 minus f y star is just this integration y star to infinity f x dx, and this side you keep it as it is. Now, what you do is you take this thing to this side. So, remember this y star is constant. So, this just becomes integration y star to infinity x minus y star f x dx, and you bring this c lambda to this side. So, you get this is equal to c lambda. So, this I have just done some very simple algebra here, so that you can easily check. So, finally, you get that the optimal value of y star will satisfy this relation, right. So, that is the optimal value or the, so remember. So, what was the problem? What is the based value of y? So, the based value of y is given by this y star, which satisfies this relation. Now, you want to find what is the maximal expected net return. For that, what you have to do? You have to just find out expectation of gy for y equal to y star, because y star is the optimal value. So, if you have to now find the maximal expected net return, so you have to just evaluate this expectation of gy at y equal to y star. So, we want to find expectation of gy star. Remember, what was the expression for expectation gy? Integration y to infinity x f x dx minus c over lambda divided by 1 minus fy. So, what you will do? You will just plug in y equal to y star. So, we do that. Now, you see here I have done a small thing that I have just subtracted and added y star. So, basically I have not done anything. So, minus y star plus y star. So, this is just expectation of gy star. Now, what is the advantage of this trick of this subtraction and addition? Now, if I just look at, so I now break it. So, one thing is y star to infinity x minus y star fx dx, right. Now, that is equal to this because y star is the optimal value. So, this will remain in the denominator. So, this first part is giving you c by lambda because of this condition. Now, the y star is constant, so it comes out of the integration. So, it is just integration y star to infinity fx dx, which is just nothing but 1 minus capital F y star. That is because capital F is the cumulative distribution function and small f is the probability density function, right. So, if you integrate the density function from y star to infinity, that just gives you 1 minus capital F of y star, fine. And this y star is constant, so it just goes out of the integration. So, the second term you get this, and this c lambda remains like this. So, this is equal to this. So, the advantage of writing it in this way is this x minus y star plus y star, that this first term I am getting that this is equal to C over lambda using this fact, and that is because this y star is the optimal value of y and it satisfies this relation. Fine. So, we get this. Now, you can easily check that this and this gets cancelled, this and this gets cancelled, and you end up with y star. So, you get an interesting thing that the maximal expected net return is actually equal to the optimal value of y. So, the optimal size of the offer that you should wait for turns out to be also your expected or maximal expected net return. So, that is an interesting thing that comes out from solving this problem. So, this y star, which is the optimal value of y until which you should wait before selling the house, and it turns out that if you follow that policy, then the maximal expected net return is also equal to that value y star. So, that is an interesting thing. You can just think about how you can interpret this. Fine. So, I leave that on you, but again it is an interesting thing that this maximal expected net return also comes to be equal to y star. Fine. So, you see, like using this concept of Poisson thinning, we have solved an interesting problem. So, this kind of problems are very real life problems, that again this kind of situation arises very often, that someone is wanting to sell a house. So, what strategy he or she should follow. So, here it gives you a nice strategy that you wait until a particular value, until an offer of size y star arrives, and once it arrives you just sell the house, and where y star is given by this particular relation. Fine. And what we needed to solve this problem, we just needed this concept of Poisson thinning, which gave us that offers of size greater than y arrive according to a Poisson process with rate lambda times 1 minus f of y. Fine. And then we just use this simple fact from calculus that if you have to find where a function is maximized, you just differentiate that function and equate the derivative to be equal to 0 and find the value of x for which this derivative is equal to 0, and then that gave us the optimal value of y star, and then we plugged in the value of y star in the expression for expected net return, and that gave us the maximal expected net return, and which finally turned out to be actually equal to the optimal value of y, which is somewhat interesting, or in fact very interesting that it is coming out to be y star. But again, I leave it on you to interpret, like you can think about why such a thing is happening, that y is the maximal expected return is equal to y star. So, that interpretation that I will leave it on you, but just I want to point out that here you get this interesting thing. Fine. Okay. So, we will stop here today. Thank you all.